Okay, so today I'm going to talk about a summary of the main aspects of Hodge theory, maybe present an application at the end. Hopefully this will motivate you to study the details that I can't go into, or if you're already familiar with Hodge theory, maybe you want to look up those details a little bit after this lecture. Okay, so the starting point is going to be, for the duration of this lecture, a Riemannian manifold, which is oriented, compact, with real dimension equal to n. Okay, now you define the Hodge star operator in the following manner. So you pick a p-form, and to such p-form you associate the star. So you pick a p-form alpha, then you associate to alpha star alpha, which is going to be an n minus p form, satisfying the following rule. So let me write down the rule. So in this rule, you pick an arbitrary p-form, and you take the inner product of beta with alpha, multiply it with the Riemannian volume, and this should equal beta wedge star alpha. Okay, and this rule should hold for all beta p forms. Now, what you need to see here is that by this rule, the Hodge star alpha is well defined. Why? Well, you have the following pairing that's non-degenerate. So you have a pairing between p forms and n minus p forms acting in the following manner. So take a p form u and n minus p form v, and you take their wedge, divide by the Riemannian volume form. So this is always a real number at every point of your manifold. So this is non-degenerate. So as such, this pairing appears on the right-hand side of this rule. You have a non-degenerate pairing on the left-hand side as well. So if you compose the non-degenerate pairing on the left with the inverse of the non-degenerate pairing on the right, that will actually give you the definition of Hodge star. Now, still, you'd want to get sort of you want to put your hand on Hodge star for calculation. So what you can do for that, choose normal coordinates, and that will reduce you to the Euclidean case. And if you do that, you will see the following. So choosing normal coordinates, right? So then the Riemannian volume will become the Euclidean volume, and then in such coordinates, right, you pick a form u, p form, so it will look like ui dxi, where I is an increasing multi-index. Right. Then what you will see, recommended exercise, is that star of u will equal sum over I of signature I ci times ui dx complementary I. So complementary I is the NP multi-index that is contained of the indices that are not a part of I, and obviously you order them in an increasing manner. So then sigma I ci will be a permutation of the numbers 1 to n that will have a signature, and that is this sigma here. So this will be an n minus p form, obviously, and that will be the Hodge star of u. Okay, good. So now that we have some understanding of this Hodge star operator, it's something worth checking that when you apply, obviously, Hodge star twice, it will be an operator from p forms to p forms. It will be not quite the identity, but almost. So it will be a identity times a power of -1. Okay, so this for all p forms. Oops. Okay. So, and again, how does this come about? Well, go ahead and check that this -1 power is nothing but the signature of ICI times the signature of CI. Okay, so next up, we're going to combine the star operator with exterior differentiation. Okay, so exterior differentiation acts on smooth P forms. And it will give smooth P+1 forms. Now, what you can do is, since we're compact, you can take the following integral. So U, B, G, where U is a smooth P form, V is a smooth P+1 form. Okay. So what you can do is compute the adjoint of D. Well, that should always exist and will be defined by this formula. Now, working through the definition of star, you end up with the following fact. So this D star, which is obviously an operator from, so D star P+1, will go from P+1 forms to P forms, will be defined in the following manner. D star will be -1 to the n P+1 star D star, where D is dP, right? And then star is the Hodge star. So you take the Hodge star of a form, sorry, n minus p here. Oops. So you take the Hodge star, take exterior differentiation, Hodge star again. Okay, now with that in hand, we can define the Laplace-Beltronic operator. Which is going to be D precomposed with D star and then D star precomposed with D. So one can see that this will act, so this will take P forms to P forms. Oops. Okay. And then sometimes we stick a P there to make sure we keep track of the index. Now, interesting thing to note. So the kernel of dP is going to be the forms that will vanish under applying Laplace-Beltrami to them. So denoted by script HP, this will be the space of harmonic P forms. Sort of our main actors for today's lecture. So first sort of interesting note about them. So suppose U is a harmonic P form. So that means that Laplace of U is 0. Okay, so what does that mean? Well, it means that d star U plus d star du is equal to 0. Okay, so now if you stick this into the inner product, and integrate, which is compact, then you will get u dvg plus, sorry, no, not quite, almost, du du, and then here star u d star u dg. Obviously, this is 0. Both of these are non-negative, so the only way they can this identity can hold true is du is 0 and d star u is 0. So if you're in the kernel of Laplace Beltrami, then both du and d star u are 0. And you can see vice versa, this is also true because of how Laplace Beltrami is defined. So you can say these two being 0 is the same as Laplace Beltrami of u being equal to 0. Okay, we'll come back to this in a minute. So the first sort of hard theorem of Hodge theory is the Hodge decomposition theorem. Okay, this says the following. So the space of smooth p-forms, global p-forms on M, decomposes as the following orthogonal sum. So the kernel of Laplace Beltrami. So this is, again, this is, as we know, harmonic p-forms. Direct product with the image of dp minus 1, so exact p-forms, and the image of dp plus 1. Okay, this being an orthogonal sum means that not only are these spaces complementary to each other, but moreover, for example, the orthogonal complement of this space is this space, and this is true for each of the components. Now, one more thing I want to add here as an addendum is the image of d star plus the kernel of d is nothing but all smooth p-forms, global p-forms. So sometimes the Hodge decomposition theorem is stated this way. Now, what you see here, so let me sure I put in the right indices. So all of these are orthogonal sums. So what you take away from here is that the kernel of dp has to be the same as the kernel of the Hodge Laplacian plus the image of dp minus 1. Okay, good. So maybe I can say a word about the proof of this Hodge decomposition theorem. It's not an easy result at all. You have to build up elliptic PDE theory to show this result. A good reference for this is Raymond Wells' differential analysis on complex manifolds. So he builds up the theory of pseudo-differential operators shows all the necessary inequalities to deduce elliptic regularity, and at the end of the day shows this decomposition theorem. Now, for us, the main application will be the following result, the Hodge isomorphism theorem. Which says as follows. So as you know, the ROM cohomology groups follows, right? So the kernel of dp over the image of dp minus 1. Okay, so from above, right, you can write kernel of dp as kernel of Laplace Beltrami orthogonal sum image of dp minus 1. When you mod out this with dp minus 1, as you're supposed to in case of the ROM cohomology, you get that the ROM cohomology groups is nothing but the space of harmonic p-forms. And this is what you gain with Hodge theory. You get a concrete representation of the ROM cohomology groups, right? So in the ROM cohomology groups, there are classes of p-forms, but in the space HP, harmonic p-forms, this is a vector space of concrete p-forms, right? So these are actual space of actual p-forms. So you can do some analysis with these, all sorts of good things. Well, I'm just going to focus on one particular aspect. Now, since the next lecture we will focus on Hodge theory and Kähler manifolds, I want to add one simple thing here. So as you know, by the universal coefficient theorem, right? So when you look at cohomology with values in C, that's nothing but cohomology with values in R tensored with C. So you can go through this whole thing and then get harmonic p-forms tensored with C. So this is HPC. So these are really just C-valued harmonic p-forms. So you get the same thing. Well, you get the complex analog that the ROM cohomology with values in C can be represented by C-valued harmonic p-forms, which are by definition just C-valued p-forms whose both real and imaginary part will be real harmonic. Okay, good. So this is something that we will come back to in the next lecture. But I want to focus on, let's stick with R. I want to focus on Poincare duality, which is a nice quick application of Hodge theory. So we have a bilinear pairing of the following sort. So HP XR, you can pair it up with HN minus P XR to give you values in R, and then you just do the following. So to such pair, you take their wedge and integrate them on M, right? So M being compact oriented, this will be just fine. So let's see that this is well defined. So for this to be well defined means that every time I stick in U plus an exact form, I should get the same as if there was no exact form here. So let's quickly see this. Now V is closed here. So as you know, you can do this. Take exterior differentiation outside, and M is compact, so you get that this thing here is 0. Okay, so indeed, this thing is well defined. Now, Poincare duality says that actually, let's call this duality star. Star is non-degenerate. And then this can be seen via Hodge theory in the following manner. So let me note the following fact, which is a quick exercise for you. So show that star and Laplace commute. Now, to show this, you just need to basically go by definition, and I will just write out what you need to check and leave it to you to check it. Right, so okay, so as you know, right, so D star is defined by -1 to the np, so D star p plus 1 star D star, right? And then stick this definition in here everywhere, being careful with the -1s, and then you should verify that. That should verify that this identity is true. Now, this says this identity, this commutation identity, that really star is going to be a certainly a map between p forms, harmonic p forms and harmonic n minus p forms. But moreover, right, because we know that star composed with star is -1 to some power. Forget what this power is, right? This is an actual bijection. Okay, so how is, and then as we know from the Hajj isomorphism, moreover, these are equal to the corresponding Theorem homology groups. Oops, what am I doing? Okay, so this alone already gives you that also these two spaces have to be isomorphic to each other. So you're certainly on the right track. But to see that star is non-degenerate, all you have to do is compute the pairing between U and star U. Sorry, not the star. So this will give you what? Well, this is U, which right, which by the definition of the star operator, this is going to be U, which, as we know, has to be positive if U is non-zero, right? So pick U being a harmonic P4, right? Which is always going to. Okay, so perhaps the best way to start here is to pick U in HP XR, which, as you know, is isomorphic to harmonic P form. So think of this U as a harmonic P form, right? Stick it in here, and as you know, so this is by definition of star. Okay, so now you get that this expression is always positive, so that means that this correspondence here is non-degenerate. All right, so that's Poincare duality there for you, just from Hodge theory. Good. So this is perhaps a good place to stop. So Hodge theory quickly implies Poincare duality. in particular, this implies what? So the fact that these two groups are the same, that their dimensions are the same as well, right? Those are often called Betti numbers. So this means that BP is equal to Bn minus B. Sometimes some books call this identity Poincare duality. Okay, good. So next time I will talk about how Hodge theory can be further optimized in case of killer manifolds. All right.